1 2 1 2 testing. So hello and welcome back to this program in which we try to understand how Zig works. So one thing that I want to do today is to try to really understand how memory works in Zig, because memory is the main thing in Zig. So in most languages you don't want to care too much about where things are, but in Zig you really need to care. So if I do something like var a, which is an int 32, which is equal to this number, like this is a variable that is on the stack, and this here, if I do const some global const variable, which is another int equal to this number, that's going to be somewhere else in memory. And if I allocate with this allocator here, this general purpose allocator, that's like new in Zig. So if I allocate with this, like an array, some array on the heap, so it's gonna be somewhere else. So it's gonna, the allocator gives me a slice of what I want, so a slice of ints. For example, I'm gonna ask the alloc for an allocation. Allocate a bunch of i32s, let's say 3 of them. So that's gonna give me a slice of i32s that I can then put things on like this. So that's gonna be again somewhere else. So how do we understand where things are? Like for example, this one here, if I want to print the address of this, I would say address of A. I want to show this, can show this as by doing, give me the address of A, like this. So, but this is not really just an address, it's like a pointer, and a pointer has also a type. So if I do this, it's gonna show, okay, so I need to try this because this could fail, because memory is an important thing and sometimes there's none left of it, so we need always to try to get some memory. So address of A is this, it's actually a pointer, so this is the actual address, it's somewhere. And if I ask for the address of some global const, it's gonna be somewhere else. And if I ask for the address of the array on the heap, address of the array on the heap, I can ask for the actual address of like the first one, like where is going to be the first one in the memory. It's going to be somewhere else again. So I'm going to show like these, maybe I should put slash ends just to show where things are. So let's look at these numbers. Is there something we can understand from these numbers? Like this looks like a bigger number. Like, so the globals, like these are actually like embedded in the executable. Like this is some region of memory. When we load the program, it's going to be there somewhere in like in the data segment of the program. And it's going to be initialized already with this number in the executable itself when it loads the .exe. If I have a variable there, instead, some global var, some other number, it's going to be somewhere else. So now we can start to think, yeah, this number, like is just after it, so it's like this. It's hard to parse. E40C. So this one, the C is a B before, so it's bigger. So these one are first. So first we have the const, then we have the variables just after all the globals, and then the A, this guy is in the stack. So this is another place completely. Like this is a big number. Like this is much smaller. Think 4, 4, 4, 4. So that's not like a good way to parse these numbers. Like I'm trying to count here, that's stupid. But like the stack is a much smaller number, so it's close to 0. So basically what I want to do is to look at like the memory, like it's just a big pile of memory. So stack starts here at this place and goes down. So the way I know that it goes down is if I do another one, I put another one in the stack, or I go in a function, some function, and I start to allocate here. See, another int, and I say I don't care about, don't bother me with that. And so I could actually show the address of B, and then the address of C actually. So I'm actually using it, so I don't care. So I can do this. So we'll try to get a feel for what the stack looks like. Stupid. That was actually an actual error that I found, but I decided not to care. So A, B, and then C in there. So let's go and call some function. Aha! I wanted the address of U. So now hopefully we'll see, yes, B, BB8. So A is here at C, and 8 is smaller than C. And then 2 is smaller than B. So we're going down. So the stack is going down like this. So we say this is the stack. And then we'll see that the heap, when I did this, it actually inside of it, like when I actually call this, it just calls the operating system, like give me some memory for my process, and Windows will decide where to put this memory in the virtual address space of the process. So it's gonna be like super high, like somewhere. So what's this number? So array on the heap, you see, it looks like some small number somewhere. And I guess we should try to guess if it goes up or down. Like try to allocate again, and then we can show me the second one. Is it bigger or smaller? You see, this is going up. So the heap looks like the heap's going to be here and going up. And then so there's going to be some region here that Windows will give us memory there. Like the stack will go down as soon as we hit 0. That's a Stack Overflow. That's how we see that we're close to a Stack Overflow. If we ask for the address of the variables we put on the stack, if we see that it comes close to 0, we're close to Stack Overflows. So that's dangerous. So that's easy to check. And then the actual program is loaded somewhere else, super high, very high. You see this number? That's a big place. So that's some big number somewhere really high in memory where we've put the executable. And so there's going to be the instructions, probably. Let's not care about instructions. Those are like in static memory. And I guess next to it, there's going to be the actual const. So that's the instructions will probably be around here. And then some other region for the variables, like these variables here. Oh, they should be here. So there's like, I guess, instructions. And then there's going to be the global consts, and then the var consts, and those like this like is stable. Like this is the size of the program. Like for any program, we know how much space will be needed for global consts and variable consts. The only difference between global const is that like they actually like that's the actual executable. You load this, and then this is going to be allocated and maybe initialized or not. But this one also about needs some initialization. It's a const, we need it to be initialized. So this one like really comes with the program. Like that's the actual like executable. Like that exe, that's this part there. But then there's the whole memory for like it's stable global memory for the program. Then there's a heap, then there's a stack. And that's it. That's where our memory is. So every time you have something, you need to think like, where is it? Because the reason why you need to think about it is because it's all manual. Like you need to think, and by thinking, you will not cause bugs. So like it's not automated like Python or like garbage collection or all these things. Like you have to think. And because of that, at first sight, it feels like a burden, and it feels like that you actually don't want to think about that. But it's gonna be like as soon as you think a little bit about it, like there's gonna be less bugs, and you'll understand what's gonna happen. And so yeah, so less bugs because you understand what's happening. So for example, if you have some function here that returns like the address of an i32. That's not an address of an i32, and I put this on the stack, and I just return the address, like return the address of this little thing. Like what's gonna happen? Like you see this, like it should like really jump in your face. Like this is like you put something on the stack, you try to give the address, you return for a function, this does not exist anymore. Like that's how a stack works. Like you just stack, and when you come back from function, you just move this little like stack pointer around, and like this won't exist anymore. So like as soon as you see this, it really should jump in your face. That's like you're gonna die. Like that's not a good thing. And it's so like basic that we don't actually think that it's a good idea for the compiler like will probably warn or do things, but like it should not even do it. Like you should not return addresses of things of the stack. Like that's basic. Like that's like programming 101. You don't return like addresses of things on the stack. So but what would actually happen? Like let's go here and just like try things. Like if I call this and I return, like I have this var return the pointer, which should be a pointer to an i32, and I call the function some function that could compile really well, and no, I have no problem. Like print, I'm gonna print this. And yeah, let's see what happens. So the return pointer, you give that, and go get like unreference this pointer. So I'm like this dereferencing the pointer. Go see what's it's pointing on. So that's the syntax in Zig to go see what's pointed by this little pointer that we got from here. So this is recipe for disaster. Like this gonna be like, ouch. Like, what? Ouch. This does not exist anymore. So what will happen? I guess nothing. Like it's actually still there on the stack. So some function ignored, blah blah blah. Some function expression value, some function. Yeah, I can't do that anymore. See, it did not do anything except like it's still there. Like we have not called another function because so it's still there. Like it's still there, but we're not allowed to use that. Like because now some other function will just like start path some other number, and I say that I don't care. That's it. Like this will, as soon as I call this, this is a void. And so yeah, I just call this new function. It's gonna like just override this stack. So I put a breakpoint. Can I put a breakpoint? Yes, please. So I'm getting here, like, and now, like this address here, like I'm getting in the function again, and so this thing, this 35, is gonna go in the same place as this one. So what's gonna happen here? Like this return pointer, it was 34. Still 34. It's because I didn't use it. So this got unoptimized out. So that it actually did nothing. So I'm gonna just print it. Yeah. Now, like he can't optimize it out. Like he'll have to put it there, put it on the stack, probably, maybe not. Like the compiler is allowed to just optimize it all out, but I'm trying to just make sure that this from some function will get polluted with this. That's gonna be a disaster. I'm here, book, and now return pointer, still 34. Really? No, it was not 34 anymore. Like it changed. You see here, like this guy here, he thinks it's 34. So the editor, like, thinks, like, did not change it. So that like there was a callback, so the editor is confused here. Thinks that this memory here. So if I do a watch again, like let's put this on the watch. Can I do a watch? Please watch. Is that a thing? No. No watching. Plus watch. Return. Still 34. But I'm like, obviously, it's still 34. So I'm actually like completely confused. Yeah, like it's always optimized out. So let's also like return, like just to make sure that we're not optimized out. So also return the, also do the crazy thing. So like these two functions do the same thing. Like one of them like puts this on the stack, returns the address. This guy puts another big number on the stack, like this, like 666, try to pollute. And now we guess that when we scrap the result, and like some function returned should be 34, but will be probably print 666. Please, yes. Okay. Now we see like we trashed this stack with other things, and yeah. So what I'm thinking is, I'm gonna show you something that I made just a minute ago, which is like let's forget about those. So I could do something like try to find like where are these things. So you see, I'm gonna have these four variables here: stack start address, heap start address, global const start address, and global vars start address. All these places, these four places, except the instructions: heap, stack, global const, global variable const, variable globals. These four places in memory that are interesting for me. and then I'll try to guess what they are. So at the beginning of the main, so that this array on the heap here, so like that's this this var on the some var on the heap, so the same thing and the heap start address is this, you see, and I do pointer to int, so to get the heap start address, this returns a usize, it gives a pointer to an int directly, so we have an address directly with an int, and so we put things in there if we want. So, and then I can do something like the first stack variable, like this would be the first stack variable. Yes, I have a first stack variable. And then like the start address, like this stack start address. Boom, stack start address. Pointer to int first stack variable, and I can see the stack start at this place, and I guess that it's going down. And then the global consts and the global vars. I'm gonna do the same thing with those. So you see, I'm gonna forget about those. I'm gonna do, that was the heap, but the globals, let's think about the globals. So this is the two types of globals we have. So that's a stack. That's the globals, consts and vars, const and vars, and then the heap. And so now we can see like these things that we can use after stack heap globals. So that's what we have now. And let's forget about this crap. Some global const, some global vars. So I need these. So first global const. So the first global const and the first global var. This and this. First global const, first global var. And I'm going to put more there so that I can test. So this is just to see where things are. So this should compile and give us blah 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 address array on the heap. Yes, obviously address array on the heap. That's not a thing anymore. So it's just var on the heap. I forgot to show what the heap does actually. So heap looks like this. Var on heap. Heap start address. I need the heap start address, which is what? Heap start address. I did that already. What? Yeah. Start here. Var on heap. Heap start address. That's the first one. Boom. That's the beginning. That's the first thing we received from the allocator. And the second one we don't actually care. It's just to show here that it was going up. Hopefully now we see address for the stack starts. This is broken. Clear, please. Stack starts here. So you see that the little syntax here is just because I know that there's going to be at most 12 of those, because this is 12, 1, 2, 3, 4, 5, 6, 7, 12. And I'm going to pad with 0, so that's why there's 2 zeros here, and I'm going to align to the right. So aligning to the right and hexadecimal. So that's the syntax to have this usize as an hexadecimal padded with zeros aligned to the right, so that they can see the address and see that very clearly that this is smaller than this. And this here is bigger. Like you see the global variables are pretty like far away, like this C, like that. It's a couple I don't know, Ks or megabytes, or I don't know. care, but it's a big number so they are here, like they are higher than these global const, variable const. And then the heap looks like this. Heap starts here. See the heap? This number, it's right in the middle, like between the stack. The stack is here, the globals are here, and the heap starts here. See this number 0, 2, 0, 0, 7f? It means the heap is in the middle here. That's important. That's but not really important, but we need to know that they are somewhere. We need to think a little bit about where things are. So now we see it. And now with this, I'm going to introduce more variables just to test, but before that I'm going to make this fun little function, because you want to see things as you make like little utils to show things. So I'm going to make this little function pub function, just a function, print type address and value. Like I'm going to receive something like some pointer to something, so any pointer. So I'm going to say that it's an any type. So that's generics in Zig. So I receive this. I'm going to like give information about this pointer. So like it's pointing on something. So let's print what it's pointing on, and also its type. And so there's a couple of things. Like first thing is like there's a thing that is pointed by the pointer. So let's go find it by differentiating it. So I don't know what the type is, so I can't say like really what this is. Like it's a type of, that's what it is. Not actually need to type this, just because I really like to show what things are if possible. So and then it's type of the thing, which is a type. It's something that is defined only at compile time. So this, we don't actually have it at runtime, but now we have it. So it's the type of thing. It's this, like this. And we have an address, which is a usize, which is using this compiler function to int. So now we have an address, a type, and a thing. So like everything we might want to care. And I want to just show the address. So I'm going to print first the address, and maybe I'm going to print, so that's the address. And afterwards I'm going to print just the type, and then let's give also the name of the variable. So I'm gonna call it like this. I want to see like a new thing on the stack. I'm gonna do something like, what I want to do is var path, which is an I32 equals this number, and I want to do give me information about this thing. Like, what is this path? I want to say path, and I'm going to give the address of path, so I can see where it is in memory. Like, is it close to the stack? So like just inside this function, we should be able to guess where this variable is. That would be fun. Like if inside the function we can like look at this pointer that we got and say, oh, this looks like it's in this region of memory, so I'm guessing that it's in the heap, or I'm guessing that it's the stack, or I'm guessing it's the globals. So that would be fun. So I'm going to print the name of the variable, and with this this column here, and then the type. So the name will be with an S, and then I'm going to go equals, and then just try to print with any, like when you give this any, it's going to try to print it whatever way it can. So but it needs to be a pointer. No, it needs to be whatever. So like try to print this. So the first thing is name. So I gave the name here. So name. Normally, the name is a like slice of things that you can of U8s that you can't modify. So that's a string in Zig book. Like most basic way, it's a view. It's a slice. This is a view on some memory. That's so we don't give the actual memory of the string. So that's just memory that some slice of U8s that you can't modify. So that's like we see this little thing here. We see it all the time. That's a view on characters. U8s could be characters or just numbers. It's you can view how you want. It's chars. So name, and then the type also will it's the type of the thing, and then the thing with any type of the thing. Here I'm putting nothing because it's gonna like it's the type, and a type at compile time will know how to print itself, so we should see the type. So just like this, we should be able to see where it is. Okay, so what's happening here? Thing, type of, yeah. Aha. So at this address, we see path, which is an I32, and with this value. So that's kind of useful. You have something, you just like give me information about it. Like it's an I32. This is a value, this is where it is. So I'm guessing that now, like because we see like if this number is like smaller than the start of stack, we can guess that it's on the stack. So I'm gonna do this. I'm gonna do like after printing the address, I'm gonna say if address smaller or equals than the stack start address, that means I'm guessing that it's in this on the stack. So I'm going to print like that and it's going to go after like this number here. So like we're going to show this number and also this value, but relative to the start of stack. So I'm going to stay like stack minus this some number and put this in no, just in parentheses, I guess. Parentheses like this. Okay. And yes, like this. And I'm gonna put stack start address minus the address that we just got. So we'll see probably that this here, like this guy, f is stack minus 284. Why is it so far? Because there's a bunch of local variables here. So it's not the first one. So this is where we are in the stack now. Because we had already all this and this and this guy. They're all like taking place on the stack. But now if I give, what I want to do is like, there's another like, other const, like this const. Hello. I am a const global and I am whatever you blah blah blah, 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 blah. So where are you gonna be? So I'm gonna do like this guy. Is like the second like global const, so it should be a little bit bigger than this guy. So I'm gonna try to print this. And yes, I forgot to do something like yeah. So I'm a account global, and the address it's not easy to parse. So this address, you see, it's just after this one. Is it? We'll see, because now I can do the same thing. I can do the same little trick. So if I guess we should start with the variable const. So if the address is bigger than the first variable const, so let's, I'm var global this is var global, so should here I want to do something like now if else if the address is bigger or equals the first global var start address. That's what I want to do. Like if I'm higher than this line here at the beginning of the variable globals, I want to show it this other way. I want to actually print this. Boom, global vars plus this, so address minus global var start address, and then same thing with the global consts. So if this is not bigger than this one, I will try with this line. So global const address minus global const start address, this one. And then, so if you're not here, like, or you're not like down there, it's you're in the middle somewhere here. So you're probably on the heap. So, or maybe the first thing that you get when you ask for the heap should be the beginning. So like in here, I'm not sure what can be there. So I'm guessing that you should still be bigger than the heap. I don't actually care. Maybe the allocator, I don't actually know. So I'm thinking that we still need to be bigger than the heap start address to see that it's the heap plus this. And yes, so that's how we show this. So now like we can look at the var on heap, like this second one, run heap 2. Let's ask for the first one in the array here. So we have something on the stack, something on the const global, something on the var globals, and something on the heap. Now we can see, like, by calling this, you get like, ooh, heap plus this. That's actually, you know what? Am I confused? Like the heap starts at this. Did I do something wrong? It's bigger than heap start address. So why did it print heap address bigger than global var start address? Global var start address, first global var, first global const. Why? So the heap is actually, it's smaller. Why? The heap is smaller. Why did you? Address bigger. Something is weird here. Hello, Macons Global. Give me, why did you say heap plus this? I'm under the impression that goes up. Is it true that it goes up? Address. There were 9. Okay, let's forget the word address. There's address. Starts at here, starts at here, starts at here. So we can parse a little. Sorry. Let's try again. This is wrong. Why? It's not heap plus this big number. It should be global vars. So this number, let's look at this number and this number. We agree that this is bigger than this. Is it? No, it's not. This one is smaller. So it's going down. Why? Ah, sorry. It's just a little typo here. Oh, so these should be first. But you see here, that's kind of wrong because I'm doing this, but like I'm using a var here. So those should be at the top, like completely at the top, even at the top of these. So let's put those here, top completely, even before std, because this is a const variable, and those like take space in the data segment of the program. So those should be really first. First global const, first global var. Ah, this should make more sense now. Okay, so we see that the var global here, it's global var plus 24. So we're in the good region. I'm account global. That's wrong though. That's still fucked. Why? I'm accounts global. You're not bigger than global consts. Global const. What is this number here? It's C1 something. It's DC1. 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 DC1BD. DC1C0. So this is bigger. This is definitely bigger than this. DC1B. DC1C. Why? It's like, why? Why? Bigger? Ah, my God. It's const. Still copy paste error, like it's copy paste error all the time. All the time. Oh, so this is gonna work, please? Yes. I'm account global, so I can so now this function is able to guess where the memory is. Yes. Yes, it's fun, it works. And now we can like, there's like this print here is not like optimal because any like if I do like one thing that's interesting is arrays. In Ziggs, like first like arrays are weird. So like but the first thing to understand with arrays is that or if you want to have just a simple array of like 3 I32s, you can say undefined and then say that the array my array equals 3 and my numbers are these 3 numbers. And that's it. So that's how you could say I32s. So you define and you initialize. And one thing, if you want to do this immediately, boom, you can do that. So that's also possible. Just 1 second. And yes, so this is so what happens when we try our nice little function with that. So what happens if I just do this? So I need the address of this array. So what will happen there? So Oh my God, that's annoying. So on the stack, so this is literally on the stack. Like the address of this, that's a variable on the stack with some number, so we know the size. So we can't have a variable here, so we know it. Again, we don't actually have to do this. The compiler can guess it, and also the compiler can guess how many numbers there's going to be. So this is still the same thing. It's literally sugar, what we just did. So this is an array on the stack. It looks like this. It's on the stack minus 316 like this. Boom. Now I can have a slice, like var slice on my array. Or let's forget about slices. Just a pointer, like a pointer on the number 5, on 5, like this 5 here. Okay, so I can say like it's gonna be a pointer, a multi-pointer, because there's like, or let's say just a pointer on I32. I say that it's the address of my array. What? The address of my array 1. So that's the pointer on 5. So this. Pointer on 5. So now what's gonna happen? Like, what's the type of this? The type of this it's this. But now we don't see it here. So we see like our thing here is a pointer. So when we do this, like the address of the pointer, it's like twice. We go twice address of the address. So address of address, it means that the value looks like this. So what I want to do is, like when I give this, I want to actually see also what it's pointed by. So the trick for this is to go deep and like look at what's in there and see if it's a pointer. We actually go and call this recursively on what's pointed by. And that could be useful sometimes, because you will see that sometimes, for example, with strings normally, with string literals, it's always like pointed by twice. So it's going to be useful to see what is pointed by. So what we're going to do is we're going to go and look at the type info. Like looking at this, like the type of the thing, we can know if it's a pointer. And the trick is, like, let's get a type info. So const type info. So type info is something that happens in built-in. It's type info, and we get it by calling the compiler function type info on the type of the thing. So this thing, like we give it a type, and it's going to give us the type info, which looks like this. It's a union. It's a union of these, so it can be one of these. So type info will return one of these things. So, and now we can switch on this, because we switch on unions like this. Switch on the union, and if it's a pointer, so a switch looks like this, we give it a block like this, and else we don't do anything. And if it's a pointer, like, does this compile? Not sure. Yes, it compiles. So if it's a pointer, you can say like print points to, and we go down another line just to show what like what's it pointing to, and we're gonna like recursively call our function with the name of the thing is pointy, like what the thing that is pointed, and we give what? We give the actual thing, because the thing is a pointer. So like we know it's a pointer, so we give it. Like the thing is a pointer, so this should compile, because it's in this switch case, the thing should be a pointer, so when we like ask to dereference it, it won't crash at compile time. So the compiler will accept that this works, because this here means that there's going to be a copy of this function made for each type, so each of them needs to compile. So point 2 arguments points to, yes, that's true. So points to this. So when we see here that the value is a pointer, we'll see also points to some other place. So some other place on the stack. So here we had this guy, which is on the stack, and this, which is not on the stack. And now this is the moment where we look at strings a little bit. So if we do string literals, const string literal my string, what it is, string literal, it's actually a pointer to a slice, which is null terminated, like let's say a pointer to a null terminated slice like this. Actually, normally like you just write this, hello, that's it. That's my string hello. You could put it wherever you want. Here, like as a global, if you just do this, the sad thing here is that like it's not clear where it is, like where is this? And now with our little function, we can actually know. So I'm going to just call this, and all the mystery will disappear, because this is like very simple to read, like, oh, my string, it's this, but what is it actually? Now we can call our new little function that will tell us what is this thing. It's called the string literal, and I'm gonna spoil it for you, but let's not spoil it and just look and understand where it is. So now we'll finally see easily where is this. It's a clack clack clack. So I can actually now I can see it. I know that it's a pointer to const 5 terminated with a 0. So that's an array that will have 5 things and then a 0. So that it's actually an array with 6 things in it, and at the end we put this. Those are U8s. So this also compiles. And the value of this, when you dereference it, you get this. So because there's a pointer here, so we get this, and this is what? This is actually this. So it's actually so it's a pointer. So when I do this, it's pointer to pointer, like, and that's why we got into this part here, and we recursively went into, and we see the pointy here. And where is it? It was here. I said const, but if I say var, it also works. So now, like, this thing will be a var, so it's going to be on the stack. So here we're on the stack with my little variable called my string, but it points to global const pointy. So what it means, it's when you write this, it actually, what is actually happening is it puts a new const thing here. So it's exactly the same thing as if I did const hello, and I said give me string 2 equals, give me a pointer to hello or just hello. Is that a thing? So let's look at what they are. Lots of printing of the string 2. So we have two strings, 1 and 2. This one is the one we discussed. And now I'm claiming that the other one will do kind of the same thing. So that's my string. It's on the stack. It looks like this. Points to this, which is global const plus 32. Pam. Hello. And the other one points to hello, which is not the same thing. It's just this. This other string, which is not the same as this one, but it goes to point to this global const plus 32. So it looks like it's the same. And this is the magic of the string literals. Just saw that it's the same one. So if we just change it, hella. So now it's going to be a different one because you can't reuse the same. So boom, oh, global const plus, ooh, it's a big number there. Yeah, so the globals are like, they're getting pretty big. So this guy here, this my string hella went somewhere in the global const really high, like we're here, like close to the variables, I guess. Okay, and this one points to like right at the beginning of this const address space, and we see the string. The other thing we can do is, like, because these numbers here, that's the normal way to show an array of uints, but we might, like, uints, it's fun to see them as these strings, so that's also easy to do. Let's go in here and say that if it's an array, because pointer is not the same as an array, so we see here, where a pointer, it looks like this. When you're a pointer, you can know, like, you're pointing to which type. You can know if you're a many type pointer, you have a size and you have a sentinel, so that's the zero terminated thing. So that's the multi-pointers thing. But array is different. It's just this. It's really simple. Array has the length and the child type and also an entity type for the sentinel. So array also has a sentinel there. But there's less thing than pointer. Pointer has alignment, volatile is const, allow 0, size 1, many, slice. So the type of pointer is a 1, many, or slice. So a many pointer has no length, points on many things, and doesn't know where to stop. Slice knows when to stop, knows to start and when to stop. So a slice has more information than a mini pointer. There is also the length. But anyway, so like now we switch, and when it's an array, we want to do something different. We want to also say that in parentheses, like, because it's if it's a U8, like we could ask if it's an array of U8s. How do we ask for it? We could add the type info what dot array. This thing, this we say that it's an array. We know it's an array, so we can say this. If we do this without asking first if it's an array, it's gonna compile time crash. And the child type if it's a U8, then we can print it with a pretty printing of U8s with the formatting specifier S. So I'm going to put in parentheses this formatting specifier here. I guess we could like also show that it's a string, like it's keeping these little quotes and saying give me the thing as a string with quotes and parentheses. So now you can actually just directly So I'm pointing on hello here. So this is hello. And the other one was hella. And it's a different place, but it's still in global const. So it means that when we did this at first, remember when we did this thing, and return local crap, but actually if we try to return a slice, sometimes you just return, we want to return like strings, like slice the const u8s, so that's a slice of like, that's a string, but that the person that calls this will return something that we won't be able to modify. But if we were just return what? So this is something that, like, you see this in C or C++ or like, what is this legal? Like, this looks like a local variable, and this is like, when you're used to C, you think this is not legal. Like, this feels very local to me. It feels like a local thing that you return a pointer to it. Like, this looks like a pointer. That's a slice that does not own the memory. So is this legal? Turns out, yes. Like this, you say just var slice of u8 equals return local crap. Boom. Print this. No problem. I'm gonna try to print this as a string. No problem. It's gonna call what, and it's not a local variable. And the way to verify this is to call our little handy little function. Boom. Just to see where it is. And we'll see. Oh, it's this little guy here. Book. And we got this from a function that felt like we were returning local things, but it's a string literal, so it's gonna go there with the other global variables. Derivance in one type of thing, type of what? Oh, I did the thing that I'm not allowed to do. Huh. It was a pointer. So I'm not allowed to do this. So this is not the same as saying this. It's compiled. So it's not the same. Okay. So a slice, you're not allowed to dereference a slice. So we should do, if I'm a pointer, I should do this only if I'm not a slice. So if type info pointer size equals just one or many is different than slice. And then type info pointer size slice when you're a slice, you're not allowed to dereference it. You need to be an actual pointer, not a slice, to dereference it. Size, pub counts, why? Not happy with that. Not happy, name side pointer. Size? Oh, it's size. This little size. So points to. So now when you're a points to. So when you're a slice, you want to do what? We're not allowed, we can't send that directly. So we can't like recursively go and print the slice. I don't actually know what to do now. Like this function really wants to dereference it. So if I'm not allowed to do this type of thing. I'm not allowed to dereference a slice. So if I just give a slice to my thing, it just breaks? No, but it's just this pointy. Feel like I just want to do this. It's probably very stupid. That won't work in general. Points to what? Feel like I want to cast it to a pointer instead. Is that possible? Can I do like pointer cast or something? Here, cast. Can I give? I want to have a type of thing. No. This type, unitype, this type, unitype, computer. Oh, I don't know what to do now to see the slice, I guess, because there's no. Pointer to this. I have no idea if this can work. Discard const qualifier. Yeah, const. Yeah. That's stupid. So now I'm not able to see what it's. So now this is points to. Like this thing equals this. It thinks that it points to something, but it's not. So we don't actually need this. So let's point to this because it's a pointer. This is not a slice. And this is actually what we want. The only problem is that we don't see the string. The only problem is that this, oof, the last one is literally this. I said it's a slice. but taking the address of the slice gives me this type. But if I did not, it's actually not that. Like it's I'm not like, if I do this without trying to be too clever, then it's gonna work immediately. No, it's still a slice because here I returned the slice. So if you're a slice, if you're this, if you're else, let's just do this. Why can't you just do this? That's cool. No, you're not happy because array, it's in your array while pointer is set. Yeah, obviously. Ha, okay, it was long, but yes. So when you're a pointer, you can still get the child. If you wait, do this. You don't need to go and even as a pointer, you don't want to like go find the address of this. But we actually are, like, we're not having what we need now. We did not prove that this poof lives on the where we think it is supposed to live. So let's kill all this just to like reduce a little bit our output. We want to find a proof that we are on the global location. So let's just, this is not enough. Like we need for the I want to call print address value of something. Pointy thing. Thing is I need to cast this to something that this guy will be happy with. So I actually did that a little bit. Like it was trying to cast this to what it can deal with. So it was the pointer cast thing. Like ptr cast to this pointer to const type of thing. No, it was type of 4-pointer child thing. Child pointer of this. Meh. So I don't actually care about this. I wanted to see it like, yeah, like this one could stay. Let's because the other one won't be able to see the thing. We'll see the thing before for this case. For if it's a slice like this, we'll see it like this. What? Because now this, we see it like this. Points to global const pointee U8. So we'll see like only the first letter. It's really just because of this. Anyway, that's enough, I think. Like the important thing is this. The string literals are cool. They work. We can know where things are in memory. We're happy. That's fun. Yes, so that was what I wanted to do today. How much time did I talk? Talked for more than an hour. It was fun. Thank you for watching. I'm not sure what I'm going to do next, but we'll see. Bye.